Hello, this is Michael Sinenko again. Now I'm going to be teaching you or telling you guys about finite differencing. This kind of builds off the last two videos. In this video, I'm actually going to be looking at how heat flows through an object in one dimension, one spatial dimension. So finite differencing is a computational method that you could utilize when you don't have as much knowledge in terms of multivariable calculus. In terms of us, because we've been using partial differential equations, we looked at the partial differential equation for the heat diffusivity in terms of the rectangular coordinates and the spherical coordinates. So this computational method is actually going to be looking at, taking small increments in terms of the time and the position, and how you can look at those increments in terms of the equation of how heat is evolved within an object. In our case, this object is only going to be one-dimensional. So I'm going to go ahead and just draw this type of object, and it's going to have it's going to go 0 through 9. So yeah, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and we can just break this up, honestly. And here we go. We have this. And what we could do is we could divvy this up. We can say that this small little change right here is going to be 0.1, which is actually going to correspond for a nice 1 meter. If this was 0.1 of a meter, from 0 through 9, it would be nicely and evenly divvied up here. And we could also do this with our time, which is going to be 0.1 as well. Now, this is entirely arbitrary. It doesn't have to be 0.1. It doesn't have to be, it can be anything. It can be 0.0005 or whatever. But the point of this finite differencing is actually you're looking at things, in terms of steps from here to here. So that's going to be 0.1 to 0.2, unlike a continuous type of understanding that you would see in traditional calculus, when you see for example, instantaneous rates of change of a function and every single number that could possibly exist between. So in this case, so yeah, we're going to look at these increments. It's a nice computational method, like I was just saying, to see how the heat is evolved within an object. It is best to actually utilize a program such as Collaboratory, which is a programming language, or it has a bunch of different it's Python based. You can use you can import different kind of libraries. It's something that we're going to see here shortly, where we're going to actually solve for how heat is being introduced into a system and how it's changing within that system. So now that we defined our volume here, what do we do? How do we actually set up this finite differencing type of equation? So we have our increments. That's cool. All right. So if you guys recall, we worked with the rectangular coordinates for our heat diffusivity. And the thing is that that was a generalized equation. For this purpose, we're actually going to look at the equation where it is when you keep the heat diffusivity constant. So it's going to be the partial of x dx plus partial, these are second order derivatives, by the way, y, and by the way, it's not x. This is going to be looking at our temperature here, dy squared plus, and I'm doing it again, and dz squared plus the heat generation divided by our heat conductivity over 1 over our alpha, and alpha is the heat diffusivity, which I'm about to define what that is, times the gradient of our temperature in respect to time. Now, the thing that I just said is this is going to be rectangular Cartesian coordinates, and we're only going to look in one direction to keep things simple. We're also going to assume that there's absolutely no heat generated within this system. So if there's not going to be any change in the y or z direction, and we're not going to have any kind of heat generated, there's actually a bunch of terms that can just cancel out. So we're not going to be looking at this one, we're not going to be looking at this one, and we're not going to be looking at that because of what I just said. And eventually, so what you're going to end up having is this second derivative of time in respect to the position, and you're going to have this 1 over alpha term, but just, to save some time, I'm going to end up putting this over here. It's going to multiply over, and you're going to have the gradient of temperature in respect to time. Okay, so this is what we got now. What do we do with this? Well, like I said, I wanted to define what this is. This was 1 over alpha. Well, it's going to be basically 1 over, and alpha is going to be our heat conductivity divided by our density times our specific heat capacity. Well, since we can just use our knowledge of algebra, we would know that this, if you were just going to have alpha instead of 1 over alpha, this would be the multiplicative inverse of that. So this is going to be equal to rho Cp over K. Just so you guys know what alpha is, it's not just some random term that you haven't ever seen before. So now that we established that, we can erase that out of the way. So how do we actually set this up in terms of finite differencing equation? So we have this part and we have this part. This one is in respect to time. This one is in respect to position. Well, what we can do to set up this equation differently is we actually need to put this into a form where we can find this in terms of a finite difference. Where, this could be our delta x distance from here to here. And it could be stepwise throughout our object. You know what I'm saying? Well, what we can do is we can say that the time to n, and it's going to have a subscript of j. So what does this mean? Well, that j term is some position in this object, or any object, honestly. So that's position. And n is some time. So what we can do this, utilizing like finite differencing type of understanding of this, we can actually, if I was to draw a number line right here, we can say at some position and some time, there can be, obviously, we keep the position the same, since this is a partial derivative and we're only looking how the time changes, we can see the position above it, so it's going to be n plus 1, and the one behind it, which is n minus 1. So we can set this up as, okay, well, we have some time at some temperature at some position, and it's going to be that time a step ahead, or some time ahead, minus the time previous to it, tjn. And we can basically divide this by the change in time increment that we had established. Like I said, that could be arbitrary. Well, that basically, look, that takes care of this whole entire term right here. We got that. And what we could do now is we could break this up. Now, how do you actually read this? Well, it's second order. So that's the same thing as, you have the derivative of a derivative. And when you have the derivative of a derivative, you can honestly just take the difference of it if you look at it in terms of a difference quotient there. So if we actually break this down in the same kind of respect here, have the same number line here, instead of keeping our position constant while changing the time, we're going to do the opposite. We're going to have our temperature as the position changes, keeping the time constant. That's just the J, the initial one that we're looking at. And right here, the temperature at some position ahead, keeping the time the same. So what we can do is, like I said, it's going to be the difference of those. So you can basically say, okay, well, we have, let's actually copy this down so it's here. And I'll have this minus delta t and the alpha there. So we will actually have, we'll have the time, the temperature at some position ahead, keeping that time, minus the temperature at the position that we are establishing and we're trying to look at, keeping that time the same, divided by the change in the increment that we decided on, which was a 0.1. And we can put this into another bracket of parentheses right here, minus the other end of this. So you would have the temperature at some position J, some constant time, and then we would have minus the temperature at some position -1, keeping that time the same, divided by delta x. And then of course, since we're comparing both of these derivatives together, and I said it was a difference, and this whole entire thing is going to be divided by delta x. Well, using our knowledge of algebra, essentially this is going to have the same denominator. So what do we know? This is actually just going to be delta x squared. So if we actually clean this up a bit, I can remove some of these things here instead of erasing a ton. This delta x can actually eventually come out in front right here. And it's going to be delta x squared. So we can get rid of that here, we can get rid of that here. And if we do some algebra here, this minus this, because this will be distributing the minus, this will become minus T2TJN. So we have minus 2TJN. And since it was a minus of a minus there, it becomes a plus. So plus Tj minus 1 n. And then that's going to be that part of the equation, you know, and how that changes. Well, we can also clean this up a little bit more. We can multiply this delta t by, just because if we have the delta t here, these will cancel if it's over there. That delta t will end up over here. So we can remove that and put that over here. And also what we can do is we can add this over there. So it's going to be on that side. And there we go. Oh no, the plus. The plus is going to be right here, of course. And so that's our final equation. So what this is saying is that the temperature at some position at some time ahead of what we're looking at is equal to that temperature at that position at that time, plus, which we're going to actually define this as one single variable when we go to code this, but it's going to be plus the product of our increment of time multiplied by the heat diffusivity divided by the square of the position. And that all of that is multiplied by the same logic. You know, this is going to be the position plus 1, you know, ahead of the one that we were talking about at the same time. At the same time, all these times are going to stay constant, minus 2 times the temperature at that, minus 2 times that temperature at that position, plus the temperature at that time where it's going to be the position minus 1 at that location. And that equation we're going to be able to code into our computational method, whatever that is going to be. You know, Python collaboratory, for us it's going to be collaboratory, and we're actually going to see how this plays out in understanding how heat is evolved within an object. So if I actually erase all of this, since we don't need it, real quick, we can have some sort of object here. And it can have any kind of arbitrary length, L. And we can actually change the parameter of, our delta x here to anything that we want. Since it's going to be a computer that's going to be doing this, it can obviously handle the calculations versus if you were to do this by hand. So that's why we do things like this on Python or Collaboratory. And we can also do the same thing with the change in, or the increment of time. So it could be, you know, very, 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 you know, small changes, and you could see how those small changes occur and what's happening and how that heat is being evolved within this system. So basically, if we had this bar and it was like a uniform temperature of 300 Kelvin, and we were looking at it, and let's just say, okay, well, that's what it is for now. So we can say at this end and at this end, okay, right here, we're going to introduce 350 kelvins and through conduction. And we're over here, we're also going to introduce 400 kelvins of conduction. And so, cool. Now we can use this and we can see how heat is being evolved as a function of time and temperature. How heat is being evolved as a function of position, incremental position, and incremental time, not temperature. Through this equation using this finite differencing equation using computational methods. I hope that clears up how this works, and I want to thank you for watching. Thank you.